Hi everyone, today I am going to introduce Teddy, an efficient SIMD-based little matching engine. As the PPT shown, my presentation is mainly divided into four parts. Firstly, I will give a background briefly. Secondly, I will introduce the core design of Teddy. Then I will show the evolution result. Finally, it will be a conclusion. Multi-stream matching has two main stages. It will firstly go through the FDR. After we found the string, then we can trigger the corresponding, more complex regex matching. As we learned, deep packet inspection is key functionality in the Layout 7 at working application, and the real expression machine is at the core of DPI. Also, the prefactor of regular expression is necessary part for performance. The representative programs are Snort, Suricata, Hubscan. For the multi-stream matching, AC is the common algorithm. In addition, we proposed an algorithm called FDR in previous paper. This is the fastest multi-stream matching at present. The grouping strategy of FDR is to sort the string into different buckets according to the order of dictionary names and match it by names of suffix to find the candidates. FDR also have some limitation. It's good for large scale, but for small scale because of grouping by string names. However, we find that the large-scale string is not common in the actual scene. For example, 90% of model security is small scale. What's worse, FDR can only handle 8 bytes by using instruction, and therefore we need a faster filter tidy. The grouping strategy of tidy is different from FDR. The principle is about suffix similarity. According to the FDR rules, ABCDE should be grouped with ABCGF, but after using the new grouping rules, ABCDE will be grouped with EFGDE. In addition, the next range of suffix matching is from 1 to 4. Through experiments, we found that 3 is the most suitable length of a suffix. In order to judge whether two strings are in a budget, we propose a scoring algorithm. The score is product of number of bit 1 per suffix byte. If the score increase, it means that the two strings should not be in same group. For example, the number of bit 1 in D and Y is 3 and 5. The score of DDY is 45. If we insert same suffix, the score will not change after bit all. If we add a new string like MMY, the score will be 125. And therefore, the DDY will not be same budget with MMY. In this section, I will introduce the design of shift-all. For multi-string matching, single-string matching has a similar principle. The process of matching a single string is described on the left. First of all, we construct a table based on the position where the suffix character appears is marked as 0, and the other positions are all marked as 1. According to the input, we get the state vector of the string one by one. After loading, we can find a blue line which indicates a match. Then we can shift the state vector to get the matching position. Multi-string matching chooses the suffix string from different markets. Therefore, only one bit needs to be added to mark. For example, we added a string IEE. The black number indicates the mark of DDY, and the red number indicates the mark of IEE. Then
We also load masks one by one and shift the state vector to get a matching. Overall, it can be considered that more string matching only needs to increase the number of the bits.
However, we found a problem that 256-byte vector access are not supported. Therefore, we designed a new method about byte decoupling. It splices a byte into high 4-bit vector and a low 4-bit vector. For example, the character of D will be spliced in 4 and 6. This will change the marking of one character from one vector to two vectors. A complete string matching by SIMD is mainly divided into 4 steps. The fourth step is to load the input and get its low 4-bit vector and a high 4-bit vector. In the second step, we need to find the match of half byte. Then we convert a half byte to 1 byte. The reason for this operation is to prepare for the next step. Then we pick up the position of matching. As we can see, Teddy can handle 16 bytes simultaneously after using byte decoupling. In this part, we evaluate performance through theory. We sorted out all the operations and instructions of Teddy and FDR and calculated cycles through the latency and port. If the theory model is adapt, cycles is 5 multiplying delta plus 3. Since 16 bytes are processed at a time, the worst performance is 16 divided by cycles. Since ranges from 1 to 4, the, the lowest value is 0.7. The reasoning of the highest performance is complex, and we give a detailed explanation in the appendix of the paper. The result shows that the worst performance of Teddy was close to the best performance of FDR. In this section, I will introduce the experimental environment and the data set we used. We used Intel Ice Lake to do the numerical evolution. The complete algorithm has been shown in HyperScan 5.4.0. We used the model security dataset and selected 3 types of the inputs to evaluate the performance of Teddy. Here we show the performance comparison of AC, FDR, and Teddy. In the first 3 figures, the row unit is the type of needle, and the corner unit is the source put. As we can see, on the different inputs, Teddy at least 1 point and 93 performance improvement over FDR, and 24.85 and performance improved over AC. In the third figure, we can see that Teddy's performance will decline in large scale little. This is in line with our expectations for Teddy. In the last figure, we can find that the performance of like operation will declare with the increase of uh, matching number, but the performance of Teddy is relatively stable. In summary, Teddy has better performance in small-scale little. In conclusion, we propose Teddy for efficient small-scale string matching. The core of Teddy is as follows. Group string by surface similarity. Design better paralleling algorithm to fully leverage an SIMD instruction-wise. Overcome implementation limitations through byte decoupling. That's all. Thanks.